Picture a moment of almost impossible darkness. The universe is a mere infant, only a few million years old. The colossal fireball of the Big Bang has faded, its brilliant light now stretched and cooled into a faint, invisible whisper of heat. All that remains is an endless, silent sea of blackness, a cosmos filled only with the simplest, most basic ingredients, hydrogen and helium gas, so diffuse and dark you could travel for 1,000,000 years and see absolutely nothing. This was the cosmic dark ages, a period of profound stillness that lasted for over 100 million years, and then something changed. In the absolute black, a tiny point of pressure and heat began to gather. A whisper of gravity pulled atoms together, and then a little more, and then a little more, until a critical threshold was crossed. In a flash that tore through the silent dark, the very first star in the universe ignited. That first dawn, the moment the darkness was broken, is one of the most profound events in all of cosmic history. And yet, for us, it remains one of the greatest enigmas we have ever faced. We call these celestial pioneers population 3 stars, and they were not like the stars we see in our night sky today. They were behemoths, cosmic titans that burned with a ferocious intensity, living fast and dying young in spectacular explosions that seeded the universe with the very first heavy elements, the building blocks for everything that would follow, including planets, oceans, and life itself. But we have never seen one. Their light is too ancient, too faint, lost in the vastness of time. Everything we think we know about them comes from theoretical models and the faint, ghostly echoes we can detect in the most distant corners of space. The journey to understand them is a mystery wrapped in a series of even deeper puzzles. In this video, we are embarking on a grand exploration of 30 of the most compelling mysteries surrounding the first stars and galaxies. We will ask questions that push the very limits of our understanding. How did something form from what was essentially nothing? What did the very first star actually look like, and could it have had planets? What triggered the end of the Dark Ages and lit up the universe for good? This is not just a story about astronomy, it's a story about our own ultimate origins. The atoms in your body, the iron in your blood, the calcium in your bones, were all forged in the hearts of stars that lived and died long before our sun was even a glimmer in the cosmos. By unraveling the secrets of the first light, we are ultimately searching for our own place in the grand cosmic story, a journey back to the very beginning of everything. Our journey into the cosmic unknown begins with the very first puzzle, the true nature of the stars that broke the eternal night. Astronomers have given these pioneers a special designation, population 3 stars. To understand why they are so mysterious, we first need to understand the cosmic family tree of stars. In our modern universe, we classify stars into 2 main populations. Population 1 stars, like our own sun, are metal-rich. Now in astronomy, metals means any element heavier than helium. These stars are the younger generation, formed from gas clouds enriched by the ashes of countless previous stellar explosions. Then there are population 2 stars. These are ancient metal-poor stars found in globular clusters and the halo of our galaxy. They are the senior citizens of the cosmos, representing a later chapter in the stellar story. But population 3 stars are the true ancestors, the mythical first generation. The crucial difference is that they were formed from a universe that was pristine, a pure cocktail of only hydrogen and helium. With no heavier elements to help cool the collapsing gas clouds, the rules of star formation were completely different, leading to a reality that is almost unimaginable to us. Theoretical models suggest these stars were not just large, they were absolute monsters. While our sun is a respectable, stable main sequence star, a typical population 3 star might have been anywhere from 100 to over 1,000 times more massive. Picture a celestial furnace so immense and so ferocious that its surface temperature would be blisteringly hot, radiating most of its energy in the far ultraviolet range. Their sheer size dictated a brutally short and dramatic life. A star that massive burns through its nuclear fuel at a breathtaking pace. Where our sun will shine steadily for billions of years, a population 3 star might have lived for only a few million years before meeting a cataclysmic end. Their deaths were not gentle fade-outs, they were titanic supernova or perhaps even more exotic events like pair instability supernova. Explosions so powerful they would completely tear the star apart, leaving no black hole or neutron star behind. And in the process, they performed the universe's very first alchemy, forging and scattering the first heavy elements into the void. This leads us directly to the core of the mystery, their elusiveness. Because they lived and died so quickly, over 13 billion years ago, there are no population 3 stars left for us to observe directly. Their light is too ancient and faint, lost to the expansion of the universe, so how can we possibly prove they ever existed? The search hinges entirely on finding indirect, ghostly evidence. Astronomers are like cosmic detectives looking for clues at a crime scene that has been cold for billions of years. One method is to peer as far back as possible with powerful telescopes like the James Webb Space Telescope, searching for the unique chemical signature of their supernova in the light from the most distant quasars or in the faint glow of ancient primordial gas clouds. Another clue lies in the patterns of the cosmic microwave background radiation, the afterglow of the Big Bang, which might hold subtle imprints from the light of these first stars. Finding even a single, definitive piece of evidence would be a monumental breakthrough, confirming the very first chapter in the story of cosmic structure and setting the stage for everything that followed. That first brilliant flash of starlight did far more than just pierce the darkness. It began a chain reaction that fundamentally reshaped the entire cosmos, and the echoes of that transformation present our second great mystery. After the Big Bang, the universe wasn't just dark, it was filled with a pervasive fog. This fog was made of neutral hydrogen gas, atoms floating freely, each with a single proton and a single electron. For hundreds of millions of years, this neutral hydrogen filled space, absorbing most ultraviolet light and keeping the universe effectively opaque. But then, something happened to clear the fog, an event we call cosmic reionization. The term sounds technical, but the process was a true cosmic revolution. It was the moment the universe became transparent, the moment light could travel across vast distances for the first time. The central question is, what was the primary force behind this monumental shift? For a long time, the prime suspects have been the first stars themselves. The most massive population 3 stars would have been incredible powerhouses of ultraviolet radiation. As this intense light streamed out into the cosmos, it would have slammed into the neutral hydrogen atoms, violently stripping away their electrons in a process called ionization. Think of it like a colossal cosmic sunrise slowly burning off a morning mist, but on a scale encompassing the entire universe. Each of these brilliant, short-lived stars would have created a growing bubble of transparent, ionized gas around it. Over millions of years, these bubbles would have expanded and overlapped, eventually clearing the fog from the vast cosmic voids. This is a compelling and elegant picture, placing the first stars as the undisputed heroes of cosmic dawn. But as our observations have improved, a compelling alternative has emerged, a rival with immense power, the first quasars. Quasars are the incredibly bright cores of distant galaxies, powered by supermassive black holes greedily devouring surrounding matter. As gas spirals into a black hole, it heats up to phenomenal temperatures, releasing a torrent of radiation that can outshine an entire galaxy. This radiation is even more energetic than that from the first stars. Could these early quasars have been the primary drivers of reionization? Their light is so intense and focused that a single quasar could ionize a region of space far larger than any single star could manage. The debate is fierce. Did the gentle, widespread flickering of countless first stars slowly clear the fog? Or was it the brilliant, piercing beams from a smaller number of these monstrous black holes that ripped the veil away? The answer is critically important because it tells us what the most influential objects in the early universe truly were. If stars were the main driver, it suggests that star formation was incredibly efficient and widespread, painting a picture of a universe lit by countless brilliant beacons. If quasars were dominant, it implies that supermassive black holes formed astonishingly quickly and played a central role in shaping cosmic structure from the very beginning. This mystery is further complicated by the timeline. We know reionization was largely complete by the time the universe was about 1 billion years old, but we don't know if it started early or late, if it happened quickly or was a slow, drawn-out process. Each scenario points to a different trigger. Pinpointing the exact chronology is like trying to solve a crime when we don't know precisely when it occurred. Unraveling this mystery is not just about understanding a past event. It's about reading the signature of the first luminous objects imprinted on the fabric of the universe itself, a signature we are only now beginning to decode with our most powerful telescopes. But moving from that initial cosmic soup to a fully fledged shining star is a problem of almost unimaginable complexity. To grasp the challenge of forming the very first star, we have to forget everything we know about how stars are born today. In our modern universe, star formation is a relatively well-understood process, aided by a crucial ingredient: dust. Giant molecular clouds, rich with elements like carbon and oxygen, contain tiny dust grains. These microscopic particles are incredibly efficient at radiating away heat. As a cloud of gas collapses under its own gravity, it heats up. The dust allows this heat to escape, which lowers the internal pressure, allowing gravity to continue its work and the collapse to proceed. It's a beautiful, self-regulating cycle, but in the primordial universe, that entire toolkit was missing. There was no dust, no heavy elements, nothing but pure hydrogen and helium gas. So how could this pristine gas ever cool down enough to collapse into a star? This is the essence of our third great mystery. The answer lies in the faintest of whispers from the Big Bang itself. While the early universe was remarkably smooth, it wasn't perfectly uniform. Satellite maps of the cosmic microwave background reveal a faint tapestry of temperature variations, slightly warmer spots and slightly cooler spots. These minuscule ripples represent tiny differences in density, regions where there was just a little bit more matter than in the areas surrounding them. Over immense stretches of time, gravity began to work on these imperfections. But here's the crucial twist. The gravity that really started the process wasn't from the regular hydrogen and helium gas we can see. It was from the invisible, mysterious substance we call dark matter. Dark matter doesn't interact with light, but it does feel and exert gravity. These dark matter particles began to clump together first, forming vast, invisible gravitational wells known as dark matter halos. Imagine these halos as immense, invisible bowls sculpted in the fabric of space. The ordinary hydrogen and helium gas drifting through the cosmos would eventually feel the gentle tug of these gravitational pits and slowly, over millions of years, begin to settle into them. This was not a fast or violent process. It was a gradual, cosmic accumulation. As the gas pooled at the center of the dark matter halo, it began to compress. But without dust to cool it, how did it overcome the heat of compression? The primordial gas had one, and only one, cooling mechanism available: molecular hydrogen. When two hydrogen atoms manage to bond together into a fragile hydrogen molecule, they can release a tiny amount of energy in the form of infrared radiation. It's an incredibly inefficient process compared to modern dust cooling, like trying to cool a blazing hot engine by occasionally flicking a few droplets of water onto it. But over millions of years, this faint molecular cooling was just enough to allow the gas to slowly lose energy, contract further, and eventually fragment into clumps that could continue their inward collapse. This leads to one of the most heated debates in the study of the first stars. Did they form alone, or did they form in groups? For a long time, the prevailing theory suggested that the first protostellar clouds were so massive that they would collapse into a single, monstrous star, a solitary titan reigning over its dark matter halo. This scenario of isolated formation seems stark and dramatic. However, more recent, sophisticated computer simulations tell a more complex and perhaps more interesting story. These models show that the collapsing gas cloud could actually develop a complex internal structure, with disks and spiral arms forming, leading to the cloud breaking up into several smaller clumps. This suggests that the first stars might not have been lonely behemoths, but instead were born in small, tight-knit families of multiple stars, perhaps even the first star clusters. The implications of this debate are profound. If the first stars formed in clusters, their interactions could have been explosive, literally and figuratively. Binary star systems could have merged, triggering even more massive stars and more energetic supernova. The intense radiation from multiple stars packed closely together would have created much larger ionized bubbles, potentially accelerating the process of reionization we discussed earlier. The question of solitude versus society for the first stars is not just a matter of cosmic demographics. It changes our entire understanding of the environment at cosmic dawn and the initial conditions for everything that came after. So we have these incredible theories about cosmic titans and the great reionization, but how do we move from simulation and speculation to hard evidence? This brings us to our fourth great challenge, the seemingly impossible task of directly observing the very first stars and galaxies. The fundamental problem is one of distance and time. The light from these primordial objects has been traveling towards us for over 13 billion years. During that unimaginable journey, the expansion of the universe itself has performed a strange magic on this light, stretching it profoundly. This effect is known as redshift. The light waves emitted by the first stars as brilliant, hot, ultraviolet radiation have been stretched so far that they now arrive at our telescopes as faint infrared whispers. It's like trying to hear a symphony played in a high pitch from another continent, but by the time the sound reaches you, all the notes have dropped into a deep, low hum that is easily lost in the background noise of the universe. This is where our most powerful observatories face their ultimate test. The Hubble Space Telescope, which revolutionized our view of the cosmos, primarily sees in optical and ultraviolet light. For peering into the era of the first light, it's like trying to see through a thick fog with a regular flashlight. The very light we're looking for has been shifted into a spectrum Hubble simply isn't optimized to see. Its deepest field images revealed galaxies from a time when the universe was already hundreds of millions of years old, but the very first generation remains just beyond its reach. The James Webb Space Telescope was specifically designed to be our window into this cosmic dawn. With its massive gold-coated mirror and incredibly sensitive infrared instruments, it is the most powerful time machine ever built. It can see in the exact part of the spectrum where the light from the earliest galaxies has been redshifted. Yet, even for Webb, detecting a single, individual population 3 star is likely beyond its capabilities. These stars were so distant and their lifetimes so brief that their pinpoint light is simply too faint. Our best hope lies not in seeing the stars themselves, but in detecting the collective glow of the first infant galaxies. Clusters of these first stars huddled together in their dark matter halos. But these galaxies are also exceedingly dim. To have any chance of spotting them, astronomers must employ a clever trick of nature itself, a cosmic magnifying glass known as gravitational lensing. Albert Einstein's theory of general relativity tells us that massive objects warp the fabric of space-time. Light traveling through this warped space bends its path. When a massive galaxy cluster sits between us and an extremely distant object, it can act as a lens, magnifying and distorting the light from the background source. This effect can amplify the faint light of a primordial galaxy by 10, 20, or even 50 times, bringing it from the realm of the undetectable into the range of our telescopes. It's not a perfect lens. It often creates strange, stretched arcs of light, like looking at a reflection in a funhouse mirror. But for astronomers, these distorted arcs are treasures, providing our only realistic chance to study the properties of the universe's first stellar systems. The search is now in full swing. Teams using the James Webb Space Telescope are meticulously scanning these gravitational lensing regions, looking for tiny, red smudges that could be candidate galaxies from the very edge of observable time. The excitement is palpable with every new data release. Already, Webb has identified galaxies that appear to exist when the universe was only a few 100 million years old, pushing our cosmic horizon back further than ever before. The next step is to analyze the spectroscopic fingerprint of the light from these candidate objects. By breaking the light into its constituent colors, astronomers can search for telltale signs of their chemical composition. The Holy Grail would be to find a galaxy whose light shows only hydrogen and helium, with a complete absence of heavier elements. Such a discovery would be the smoking gun, definitive evidence of a truly primordial system. A galaxy composed solely of that first generation of stars, allowing us for the first time to directly test our theories about the dawn of light. These theoretical giants lead us directly into our next pair of deeply intertwined puzzles, mysteries that strike at the heart of what the first stellar population actually looked like and the invisible cosmic architecture that made them possible. The fifth mystery asks a fundamental question about the stars themselves. Were they all universally massive, or could there have been a surprising variety? We often picture these pioneers as colossal behemoths, but is that the whole story? This idea is tied to a concept astronomers call the initial mass function, which is essentially a cosmic census of how many stars of different sizes form in a given batch. In today's universe, this function is quite democratic. For every truly massive star that forms, like 150 times the mass of our Sun, a vast number of smaller, Sun-like stars and even smaller red dwarfs are born. The universe seems to prefer making small stars, but for the first stars, many models suggest the rules were completely different, pointing to what's known as a top-heavy initial mass function. In this scenario, the scales are tipped dramatically in favor of the giants. The physics behind this is rooted in that pristine, metal-free environment we discussed. Without heavy elements and dust to cool the gas efficiently, the collapsing cloud struggles to fragment into smaller pieces. It's like trying to break apart a massive, hot, inflating balloon with only your hands. You might be able to tear off 1 or 2 big chunks, but you can't easily shred it into 1,000 tiny pieces. The gas simply stays hotter and more stable, resisting the instability that would lead to the formation of smaller stars. This top-heavy model suggests the first star-forming clouds predominantly gave birth to titans, with average masses many tens of times that of our Sun. However, this is not a settled debate. Some sophisticated computer simulations reveal a more nuanced picture. They show that even in a pure hydrogen and helium gas, complex processes can occur within the collapsing cloud. As the central protostar forms, it can be surrounded by a swirling disk of gas, and interactions within this disk, shock waves, and competing gravitational pulls might still allow the cloud to fragment, producing a handful of stars with a wider range of masses. Perhaps the first stellar nurseries did not produce just solitary monsters, but instead small families of stars that included some more modest, though still likely large, siblings. The answer to this mystery is crucial because it dictates the entire character of the early universe. A cosmos dominated only by supermassive stars would be a place of brief, violent flashes of light followed by catastrophic explosions. A universe that also contained a population of longer-lived, smaller stars would have had more stable sources of light. potentially influencing how quickly larger structures could form, and even providing longer-lasting cosmic beacons for us to potentially detect. But to fully understand how any star could form, we must turn our attention to the true unseen architect of the cosmos, and this is our sixth mystery, the profound and specific role of dark matter. We mentioned earlier that dark matter halos acted as gravitational traps, but their influence is even more fundamental. Think of the primordial universe after the Big Bang. The ordinary matter, the hydrogen and helium gas, was incredibly smooth and spread out. It was also under tremendous pressure from the background radiation, a pressure that resisted any attempt to clump together. Dark matter, however, is ghostly. It doesn't interact with light or radiation, it only feels the force of gravity. This meant that dark matter could begin collapsing under its own gravity long before the ordinary gas could, unaffected by the pressure that kept the gas so evenly distributed. These dark matter clumps grew over time, merging with one another to form those vast, invisible halos. It was only within the deep gravitational wells of these halos that the conditions became right for gas to finally start accumulating. The gas, feeling the pull of the dark matter's gravity, would slowly sink to the center of the halo, reaching the densities necessary for star formation to begin. In many ways, the dark matter halo served as the birth cradle for the first stars. Without these invisible scaffolds, the gas might have remained diffuse forever, and the universe might never have lit up. This leads to one of the most exciting frontiers in cosmology, the possibility that the very nature of dark matter itself determined when and how the first stars appeared. The standard model assumes cold dark matter, meaning its particles move relatively slowly. This slowness allows it to clump effectively on very small scales, creating the numerous low-mass halos that could have hosted the very first stars. But what if dark matter is warm? Warm dark matter particles would move faster, making it harder for them to clump together on small scales. This would mean the first dark matter halos to form would be significantly larger, delaying the onset of the first star formation until enough matter had gathered to build these bigger structures. A universe with warm dark matter might have experienced a later, more synchronized cosmic dawn, with many stars igniting around the same time in more massive halos. The properties of something we cannot directly see are therefore imprinted in the timing of the first light, a ghostly signature waiting to be decoded by comparing the predictions of these models with the ever deeper observations from telescopes like James Webb. The dramatic lives of the first stars were inevitably followed by equally spectacular deaths, and the nature of their final moments presents our seventh great mystery. How exactly did these cosmic titans meet their end? The answer is not straightforward, as their fate was likely determined by their immense mass. For the very largest of the population, 3 stars, a particularly violent type of explosion is theorized, known as a pair instability supernova. This is not your average stellar death. In a star of several hundred solar masses, the core becomes so incredibly hot that the radiation inside it undergoes a bizarre transformation. The energy of the photons becomes so great that they spontaneously convert into pairs of electrons and their antimatter counterparts, positrons. This process is catastrophic because radiation pressure is what holds a star up against the crushing force of its own gravity. When that radiation suddenly vanishes, turning into matter, the star's internal support system catastrophically fails. The core collapses in an instant, triggering a runaway thermonuclear explosion that is so powerful it completely unbinds the entire star. There is no remnant left behind, no neutron star, no black hole. The star is utterly obliterated, and in its final, unimaginable blast, it scatters its freshly forged heavy elements far and wide into the primordial cosmos. This is the universe's first true act of creation through destruction, seeding the void with the carbon, oxygen, and iron necessary for future planets and life. However, there is another, even more extreme possibility for the absolute upper echelon of these first stars. If a star was massive enough, perhaps over 250 times the mass of our Sun, its gravity might have been so overwhelming that not even a pair instability explosion could stop it. In this scenario, the entire star would have collapsed directly into a black hole, vanishing from the universe without a supernova fireworks display. It's a silent, dark fate, a stark contrast to the brilliant, element-scattering finale of its slightly smaller cousins. Determining which fate was more common is critical to understanding the initial chemical enrichment of the universe and sets the stage for our next profound puzzle. This direct collapse scenario leads us directly to the eighth mystery, one that connects the very first stars to the most dominant structures in the present-day cosmos, the origins of supermassive black holes. At the center of nearly every large galaxy, including our own Milky Way, lies a gravitational monster weighing millions or even billions of times the mass of our Sun. The existence of these behemoths so early in the universe's history is a major conundrum. How did they have enough time to grow so immense? The leading theory suggests that the black holes formed from the direct collapse of the first population. 3 stars could have served as the initial seeds for these giants. A black hole of even 100 solar masses would have a tremendous head start, a massive anchor point onto which gas could accumulate at a ferocious rate. But here lies the core of the mystery. The growth process itself is poorly understood. For a seed black hole to become supermassive within the first billion years of the universe, it would need to accrete or devour surrounding matter at a rate that pushes the very limits of physics. This is not a simple, steady feast. As matter spirals into a black hole, it releases an enormous amount of energy in the form of radiation, which can actually push incoming material away, effectively turning off the food supply. This creates a fundamental tension. The very process of eating generates a feedback that can prevent further eating. To achieve the growth we observe, these early black holes must have found a way to overcome this limitation, perhaps through periods of hyper-efficient accretion or by feasting on dense, cold flows of gas that could somehow bypass the intense radiation pressure. The alternative to the stellar seed theory is even more radical. The possibility that supermassive black holes were born large, forming directly from the collapse of immense primordial gas clouds, skipping the stellar stage entirely. This direct collapse black hole scenario would create seeds thousands of times more massive than any stellar remnant, giving them a much easier path to becoming the giants we see. Unraveling which path nature took is key to understanding the symbiotic relationship between the first stars, the first black holes, and the galaxies that grew around them. The transition from the first brilliant, isolated stars to the first true galaxies marks a pivotal leap in cosmic evolution, taking us into our 9th great mystery, the actual assembly process of these initial stellar cities. After the dramatic supernova of the population, 3 stars scattered the first heavy elements into their surroundings. The cosmic stage was set for a new level of complexity. The question is, how did these disparate elements and the remaining primordial gas come together to form the first recognizable galaxies? Did they build up gradually, brick by brick, or did they emerge fully formed in a single, rapid event? This puzzle of structure formation lies at the heart of understanding how our universe grew from simplicity to the intricate web of galaxies we see today. The dominant theory, known as hierarchical structure formation, paints a picture of cosmic construction from the bottom up. Imagine the early universe populated by countless dark matter halos of various sizes, each one a potential gravitational trap. Within the smallest of these halos, the very first stars ignited. According to the hierarchical model, the first galaxies began not as grand spirals, but as tiny proto-galaxies or building blocks. These were likely just small clusters of stars, perhaps containing only a few thousand or a few million members, all held together by their shared dark matter halo. Over time, gravity's relentless pull would have drawn these proto-galaxies toward one another. they would have collided and merged, their stars and gas mixing together to form progressively larger and larger structures. It's a process akin to small streams merging to form a river, and then rivers converging into a mighty estuary. This slow, gradual assembly through mergers would have been a violent, chaotic process, shaping the early galaxies through a series of cosmic collisions. However, an alternative pathway cannot be entirely ruled out. Some simulations suggest that under the right conditions, a particularly massive and dense cloud of gas could undergo a rapid monolithic collapse. Instead of a slow assembly from many small pieces, a single immense cloud could fragment and form stars in a huge burst of activity, essentially creating a large galaxy in a relatively short period of time. This top-down scenario would result in a very different early galactic environment, one characterized by a ferocious wave of star formation all at once. The evidence we are gathering, particularly from the deep field images of the James Webb Space Telescope, seems to strongly favor the hierarchical model. We see a universe filled with small, irregular, and often clumpy galaxies in the early epochs, exactly what we would expect if mergers were the primary engine of growth. Yet the possibility remains that some of the earliest and most massive galaxies we are finding might have formed through a more direct and rapid channel, adding a layer of fascinating complexity to the story. This leads us directly into our 10th mystery, which asks a profound question about legacy. What is the true relationship between these chaotic, infant galaxies and the majestic, well-ordered systems we observe in the modern universe? The first galaxies observed by telescopes like Webb are a far cry from the beautiful spiral arms of Andromeda or the smooth, football-shaped ellipsoids of giant elliptical galaxies. They are often described as pebbles or train wrecks, irregular, messy, and turbulent structures blazing with the light of intense star formation. So, how did we get from there to here? Were these chaotic blobs the direct ancestors of modern galaxies, or were they merely a transient, unstable phase that had to be completely reshaped? The answer appears to be that they are indeed the direct progenitors, but they underwent an extreme cosmic makeover. The transformation was driven by two key factors: mergers and internal evolution. As these small galaxies continued to merge, the dynamics of the collision played a decisive role in determining the final galaxy type. When two gas-rich galaxies merged, the influx of fresh fuel could trigger a final burst of star formation and often lead to the formation of a central bulge and a disk, eventually settling into a spiral galaxy like our Milky Way. However, if the merger involved galaxies that had already exhausted most of their gas, the result was primarily a gravitational reshuffling of the existing stars, leading to a more featureless elliptical galaxy. Furthermore, within these young galaxies, the first generations of stars lived fast and died young, and their supernova explosions began to blow out the remaining gas, regulating future star formation and gradually clearing out the chaos. The emergence of a central supermassive black hole also contributed, as its energetic feedback helped to heat and disperse gas, preventing runaway star formation and allowing a more stable structure to emerge. Understanding this link is like tracing the family tree of a modern city back to a small, rough-hewn frontier settlement, recognizing that the core identity was there from the beginning, even if the appearance has been utterly transformed by billions of years of history. Yet, as we push our observations to the very edge of the observable universe, a new and puzzling discrepancy has emerged, challenging the very foundations of our models. This is our 11th mystery, the luminosity problem. In simple terms, our most sophisticated theoretical simulations, which incorporate our best understanding of dark matter, gas physics, and star formation, predict that the early universe should be teeming with a vast number of relatively bright young galaxies. We expect to see a cosmic skyline filled with the glittering lights of these early stellar cities. However, when we point the James Webb Space Telescope at these ancient epochs, what we actually see is somewhat different. While Webb has indeed found a surprising number of galaxies, there seems to be a missing population, a deficit of the faint, early galaxies that our models insist should be there. It's as if we predicted a bustling metropolis but upon arrival found a smaller town than expected. This discrepancy forces us to re-examine some of our most fundamental assumptions. Perhaps the efficiency of star formation in these primordial galaxies was lower than we think. Maybe the process of turning raw gas into shining stars was less straightforward in the pristine environment of the early universe. Alternatively, the light from the very first stars and galaxies might have been obscured in ways we haven't fully accounted for, perhaps by thick shrouds of primordial dust or gas that formed earlier than previously thought. Or the answer could lie in the nature of the dark matter halos themselves. If dark matter has properties that prevent it from clumping on the very smallest scales, as suggested by the warm dark matter hypothesis, then the number of potential star-forming sites in the early universe would be reduced, directly leading to fewer galaxies. Solving the luminosity problem isn't just about fixing a number in a simulation. It's about correctly identifying the fundamental rules that govern the universe's first steps toward building complexity. While we search for these missing galaxies, we can also turn our gaze much closer to home, looking for ancient relics that hold the chemical secrets of the first stars. This brings us to our 12th mystery, the hunt for the primordial pollution. The violent deaths of those first population, 3 stars acted as the universe's first and most important recycling program. They spewed their newly forged elements carbon, oxygen, magnesium, and iron out into the surrounding gas, forever contaminating the pristine cosmic environment. The next generation of stars that formed from this enriched material would carry a specific chemical signature within them, a fossil record of that first stellar generation. Incredibly, some of these second-generation stars are still shining today within the halo of our own Milky Way galaxy. They are incredibly old and metal-poor, but they are not entirely metal-free. They contain a tiny yet measurable amount of heavy elements. By analyzing the light from these ancient stars with high-precision spectroscopy, astronomers can read this chemical fingerprint. The specific pattern of elements they find is like a clue to the nature of the stars that came before. For instance, the chemical signature of a pair instability supernova is very different from that of a core collapse supernova from a slightly less massive star. Finding a star with a peculiar abundance of certain elements might be the smoking gun for a specific type of population, 3-star death. It's a form of cosmic archaeology where we study the artifacts, the ancient stars in our galactic backyard, to infer the properties of the long-vanished progenitors that created them. This painstaking work is crucial because it provides a direct, local test of the theories we develop about the first stars, offering a complementary path to understanding that doesn't rely solely on looking back to the edge of time. All of these puzzles converge on a single, critical question of timing, our 13th mystery. When exactly did cosmic dawn begin? Pinpointing the moment the first starlight pierced the darkness is one of the greatest challenges in modern cosmology. We have 2 primary ways of investigating this, and while they generally agree, there is a tantalizing tension between them. The first method involves studying the cosmic microwave background. Satellites like Planck have measured the subtle imprints that the first stars and galaxies left on this afterglow radiation. As the first sources of light began to ionize the hydrogen fog, they interacted with the CMB photons, leaving a faint record of when this process started and how long it took. This data suggests that reionization was well underway when the universe was around 400 million years old. The second method involves using powerful telescopes like Hubble and Webb to directly observe the most distant galaxies. By measuring their redshifts, we can determine their age and build up a timeline of cosmic structure. The surprising result from Webb is that it has already found galaxies that appear to be mature and massive at shockingly early times, when the universe was only 200 to 300 million years old. If these galaxies are truly as evolved as they seem, it implies that the first stars must have ignited even earlier, perhaps pushing the dawn of star formation back to a time just 100 million years after the Big Bang. This slight discrepancy might be due to uncertainties in our measurements or in the models we use to interpret the data. Or it might be a hint that our universe lit up even more quickly and efficiently than we ever thought possible. Resolving this timeline is essential, as it tells us how fast the universe transitioned from a simple, dark void to a complex, structured, and luminous cosmos, setting the clock for the entire subsequent history of galaxy evolution. As we look back towards the dawn of time, we are searching for individual points of light, the faintest of galaxies. But there is another way to search for the first stars, one that involves looking not for the trees, but for the entire forest. This is the 14th mystery, which takes us into the realm of a faint, ghostly glow that permeates the entire sky, the cosmic infrared background. Imagine going outside on a moonless night far from any city lights. The sky is dark, but it's not perfectly black. There is a faint, almost imperceptible background glow. Some of this is from our own solar system, some from the combined light of distant stars and galaxies too faint to see individually. But a portion of this faint light is believed to be the cumulative, redshifted echo of the very first stars and galaxies. Their individual lights are far too dim to detect, but together, their combined emission creates a diffuse, all-sky background, a fossil imprint of the collective output of that first cosmic dawn. The challenge, of course, is that this signal is incredibly subtle and buried under a mountain of foreground light. It's like trying to hear a single, quiet violin in a massive orchestra by listening only to the overall hum of the entire concert hall. The cosmic infrared background is a composite of light from many different eras. There's emission from dust in our own galaxy, from zodiacal light caused by dust in our solar system, and from countless later generation galaxies. Isolating the specific contribution from the very first luminous sources is a monumental task of cosmic signal processing. Astronomers must meticulously model and subtract all these brighter foreground sources, hoping to reveal the faint, residual glow that was produced in the universe's infancy. The real breakthrough comes not from just measuring the total amount of this background light, but from studying its pattern. The key is to look for anisotropies, tiny, statistical fluctuations or lumps in the intensity of this background glow. The early universe wasn't perfectly smooth. It had those tiny density fluctuations we discussed. Consequently, the first stars and galaxies didn't light up uniformly across space. They formed in clusters and filaments, tracing the underlying cosmic web of dark matter. This means their combined light should not be perfectly even. It should have a specific, lumpy pattern. By mapping these faint irregularities in the cosmic infrared background, we can effectively create a blurry, low-resolution map of the large-scale structure of the universe as it was during the era of the first light. It's a way of seeing the outline of the first cities of stars, even if we can't resolve the individual buildings. Analyzing these fluctuations is like a sophisticated form of statistics. The size and brightness of the lumps tell us about the typical size and luminosity of those first stellar systems. If the lumps are relatively large, it suggests the first sources were clustered in big groups, perhaps massive galaxies. If the lumps are smaller and more numerous, it might point to a universe filled with a larger number of smaller, fainter protogalaxies. This data provides a crucial independent check on the theories and direct observations from telescopes like James Webb. Does the pattern of fluctuations match what we would expect from the population of early galaxies we are starting to find? Or does it suggest there is a whole other population of even fainter, more diffuse sources that are still eluding our direct detection, perhaps helping to solve the luminosity problem we encountered earlier? The cosmic infrared background and its subtle anisotropies offer a unique statistical window into the grand tapestry of cosmic dawn. allowing us to sense the collective presence of the first stars in a way that complements our hunt for their individual light. But while we search for the chemical ghosts of the first stars and the faint glow of their collective light, there exists a theory so revolutionary that it could rewrite the very first chapter of cosmic dawn. This is our 15th mystery, the potential existence of dark stars. Imagine, if you will, that the very first sources of light in the universe were not stars at all, at least not in the way we understand them. What if, before the first nuclear fires ignited, there were objects powered by something far more exotic, the invisible substance that makes up most of the matter in the cosmos? This is the incredible premise behind the dark star hypothesis. A dark star would be a celestial object of almost unimaginable proportions. Unlike a conventional star, which is powered by the relentless fusion of hydrogen into helium in its core, a dark star would draw its energy from the annihilation of dark matter particles. The theory hinges on a specific property of a hypothetical class of dark matter known as WIMP, or weakly interacting massive particles. If these particles are their own antimatter counterparts, then when two of them collide, they could annihilate each other, converting their entire mass into pure energy according to Einstein's famous equation. In the early universe, where dark matter was densely packed into the first halos and ordinary gas was pouring in, these annihilations could have provided a powerful and steady heat source. Here is how it might have worked. As a cloud of primordial hydrogen and helium gas collapsed into the gravitational well of a dark matter halo, it would have pulled a high concentration of dark matter along with it, trapping it at the center. If the dark matter annihilation rate was high enough, the energy produced could have counteracted the force of gravity, preventing the gas from compressing to the extreme densities and temperatures needed to trigger nuclear fusion. The result would be a gigantic puffy ball of gas, glowing not with the fierce light of fusion, but with the soft, warm glow of dark matter annihilation. These objects could have been truly monstrous in size, theorized to be anywhere from the size of our entire solar system out to the distance of the orbit of Pluto, and with masses up to 1 million times that of our Sun. They would have been incredibly diffuse, more like a vast, warm cloud than a dense, fiery sphere, and because their power source was so steady and long-lasting, they could have shone for millions or even billions of years. The implications of this are staggering. If dark stars existed, they would have been the very first luminous objects, predating even the mighty population 3 stars. They would have lit up the cosmos in a soft, pervasive glow long before the first supernova ever echoed through the void. Their presence would have profoundly altered the timeline of reionization and the initial chemical enrichment of the universe. But the most compelling question is, could we actually find evidence for them today? This is where the James Webb Space Telescope enters the scene as a potential dark star hunter. The light from a dark star would have a very distinct signature. Because it's powered by annihilation and not fusion, its surface temperature would be much lower. A population 3 star would be scorchingly hot, radiating intensely in the ultraviolet. A dark star, by contrast, would be much cooler, and its light, after being stretched by billions of years of cosmic expansion, would arrive at JWST as a very specific type of infrared signal. Astronomers are now meticulously analyzing the spectra of some of the most distant, reddest objects JWST has detected, searching for a pattern that simply doesn't match any known type of galaxy or star, a signal that could only be explained by the exotic physics of dark matter annihilation. The search for a dark star is a high-stakes endeavor. Finding one would not only confirm an entirely new type of astronomical object, but would also provide the first direct evidence for the specific particle nature of dark matter itself. It would be a discovery that bridges the gap between the largest scales of cosmology and the smallest scales of particle physics, offering a profound glimpse into the fundamental forces that shaped our universe's infancy. It represents the thrilling possibility that the first light we are so desperately seeking was not a familiar fire, but something far stranger and more wonderful. While we grapple with the possible existence of entirely new kinds of luminous objects, there was another invisible force at play in the early universe, one that we are intimately familiar with today but whose origins remain deeply mysterious. This brings us to our 16th puzzle, the profound and unknown impact of the very first magnetic fields. We live in a world permeated by magnetism, from the compass that guides us to the MRI machines that heal us. Our sun has a powerful magnetic field that drives sunspots and solar flares, and our entire Milky Way galaxy is threaded with a vast, weak magnetic field that guides cosmic rays. But where did these fields come from? Was the newborn universe born with primordial magnetic fields woven into its very fabric, or were they painstakingly built from scratch by the first stars and galaxies? The idea of a primordial magnetic field is captivating. It suggests that these forces were created in the extreme conditions of the very early universe, perhaps during a phase transition a fraction of a second after the Big Bang. If such fields existed, they would have been incredibly weak and spread uniformly throughout the cosmos, a faint cosmic background magnetism analogous to the cosmic microwave background radiation. While weak, their presence from the very beginning would have had a subtle but crucial influence on the formation of the first structures. Even a tiny magnetic field can affect how charged particles move within a plasma of hot gas. As the first density fluctuations began to grow, these primordial fields could have provided a preferred direction, adding a layer of order to the chaotic collapse of gas, potentially influencing the spin of the first protostellar clouds and the disks that formed around them. The alternative is that magnetic fields have a more humble, bottom-up origin. In this scenario, the early universe was truly devoid of any large-scale magnetism. The first seeds of a magnetic field could have been generated by the first stars themselves through a process known as a Biermann battery. This occurs when there are differences in temperature and pressure in a plasma that is not perfectly uniform, conditions that would have been inevitable in the turbulent wakes of the first supernova explosions or in the accretion disks around the first black holes. This effect would generate a faint initial magnetic field, which could then be amplified and woven throughout the cosmos by dynamo action. A dynamo works like a cosmic generator, the motions of turbulent conducting gas, such as the rotation of a star or the churning of a galactic disk, can stretch and twist a weak magnetic field, dramatically increasing its strength and scale over time. The first stars, with their powerful winds and violent deaths, would have been the universe's first magnetic field factories. The distinction between these two origins is critical because it determines how influential magnetism was at the very dawn of star formation. If fields were primordial, they were there from the start, subtly guiding the collapse of the very first gas clouds. This could have affected the fragmentation of these clouds, potentially leading to a different distribution of star sizes than in a non-magnetic universe. Magnetic fields can provide extra support against gravity, acting like a cushion that resists collapse. This might have prevented some clouds from forming stars as easily, or it could have influenced the formation of bipolar outflows, the high-speed jets that are commonly seen shooting from the poles of young stars today. Did the first stars also launch such jets, and if so, did magnetic fields power them? These jets can carry away angular momentum, allowing the central star to form more efficiently, and they also inject energy and momentum back into the surrounding gas, regulating future star formation. The presence or absence of magnetic fields could have fundamentally shaped the efficiency and character of the very first episode of star birth in the cosmos. Unraveling this mystery is exceptionally difficult because magnetic fields are invisible. We can only detect them by their influence on light or charged particles. To probe the magnetic fields of the early universe, astronomers look for their imprint on the light from the most distant quasars. As light from a quasar travels through the vast intergalactic medium, it passes through clouds of primordial gas. If a magnetic field is present in those clouds, it can cause a very subtle effect on the light known as Faraday rotation, where the plane of polarization of the light is twisted. By measuring this twisting in the light from quasars at different distances, we can effectively look back in time to see when magnetic fields first appeared in the voids of space. Finding evidence for magnetization in the very oldest, most pristine gas clouds would be a strong argument for a primordial origin. Conversely, if the fields only appear later, associated with regions that have been polluted by the ejecta from the first stars, it would point to a stellar origin. This detective work connects the largest scales of cosmology to the intricate physics of plasma, seeking to trace the invisible lines of force that may have helped write the first chapter of cosmic structure. We've explored how the very first sparks of light might have ignited, but that immediately leads to one of the most fundamental questions about cosmic architecture. This is our 17th mystery. What was the actual sequence of construction in the early universe? It's a classic cosmic chicken and egg problem. Did the first stars form in isolation, lighting up one by one like distant campfires in a vast dark wilderness, and only later get drawn together by gravity to build the first galaxies? Or did the galaxy come first, with immense primordial gas clouds collapsing as a single entity, only then fragmenting internally to birth their stellar populations? The answer dictates our entire understanding of how complex structures emerge from simplicity. For decades, the dominant framework has been hierarchical structure formation, a bottom-up scenario that aligns beautifully with our understanding of dark matter. In this model, the universe builds itself from the smallest pieces upward. Think of it as cosmic carpentry, starting with nails and boards before assembling the walls and finally the entire house. The process begins with those tiny density fluctuations imprinted in the Big Bang. Dark matter, responding only to gravity, clumps first into small-scale halos, some perhaps no more massive than a single star cluster today. Within the very smallest and densest of these halos, the conditions become right for the first population, 3 stars, to ignite. So, in this picture, stars absolutely come first. These first stellar nurseries would have been incredibly modest, perhaps just a single massive star or a small, tight-knit cluster of stars, each occupying its own tiny dark matter halo. These were the fundamental building blocks of everything to come. Then, gravity's patient work begins. These small halos, each potentially hosting its own pocket of stars, would slowly drift toward one another, drawn by their mutual gravitational attraction. They would merge, their stars and gas mingling to form a larger, more complex structure, a protogalaxy. Over hundreds of millions of years, a series of these mergers would build up a true galaxy, like a small stream merging with others to form a river. This hierarchical model predicts that the earliest galaxies we should see would be small, irregular, and numerous, gradually growing in size and mass through a violent history of collisions and acquisitions. The evidence for this is compelling. The deep field images from the Hubble and now the James Webb Space Telescope show a young universe filled with exactly these kinds of small, clumpy, and often merging galaxies, a cosmic construction site in full swing. However, an intriguing alternative theory known as monolithic collapse, or the top-down model, suggests a very different path. In this scenario, the galaxy forms in a single, rapid, and dramatic collapse. Imagine an immense, pristine cloud of hydrogen and helium gas, perhaps spanning thousands of light years, residing within a particularly massive dark matter halo. Instead of fragmenting into many small star-forming regions, this entire gigantic cloud collapses coherently toward its center. As it collapses, it may eventually reach a point of critical density where it fragments en masse, triggering a colossal, galaxy-wide starburst. In this picture, the galaxy's stellar population is born in a single, ferocious wave of creation. The galaxy, as a large-scale structure, forms essentially at the same time as its stars, or perhaps even just before them. This would result in a very different early universe, one where large, luminous galaxies appear almost fully formed very early on, rather than growing gradually through a series of mergers. So, how do we determine which path nature actually took? The key lies in the detailed properties of the most distant galaxies we can observe. The hierarchical model makes specific predictions. We should find that galaxies at higher redshifts, meaning further back in time, are systematically smaller, less massive, and more irregular than their modern counterparts. Their star formation should be bursty, often triggered by merger events. The monolithic model, on the other hand, would allow for the possibility of finding surprisingly massive and mature-looking galaxies at extremely early epochs, objects that appear too well-formed to have been built piecemeal in such a short time. This is where the James Webb Space Telescope is causing such a stir. It has indeed identified several candidate galaxies that exist when the universe was less than 400 million years old, and some of them appear to be massive and structured. The immediate question is whether these objects truly represent a challenge to the hierarchical model, or if they are simply the rare, over-dense peaks in the early cosmos that merged with extraordinary speed and efficiency. The truth likely involves a fascinating combination of both processes. While hierarchical merging was almost certainly the dominant engine of growth, the very first stages of galaxy formation might have had a monolithic character within individual dark matter halos. A large halo could undergo a rapid, coherent collapse that forms its first generation of stars in a relatively short burst, establishing the core of the galaxy. Then the hierarchical process takes over as this core galaxy begins to accrete smaller satellite building blocks, growing in size and complexity over billions of years. This hybrid approach reconciles the apparent maturity of some early galaxies with the overwhelming evidence for mergers we see throughout cosmic history. Unraveling this sequence is not just an academic exercise. It tells us about the fundamental rhythms of cosmic evolution, whether the universe built its grandest structures through slow, patient accumulation or in sudden, violent eruptions of creation. While we search for the faint light of the first galaxies and the ghostly signature of dark stars, there is an entirely different way to probe the cosmic dark ages, one that listens not for light, but for a specific, low-energy whisper from the hydrogen gas itself. This is our 18th mystery, and it hinges on a single, predictable quantum jump inside the most common atom in the universe. Every atom of neutral hydrogen consists of a single proton and a single electron, and these two particles each have a property called spin. Think of them as tiny magnets that can be aligned in the same direction or in opposite directions. The state where the spins are parallel is ever so slightly more energetic than the state where they are anti-parallel. Once in a great while, about every 10 million years for a single atom, an electron will spontaneously flip its spin to the lower energy state, releasing the tiny difference in energy as a photon with a very specific wavelength, 21 centimeters. This is a radio wave. On its own, this event is incredibly rare, but the early universe was filled with a near infinite number of these hydrogen atoms. Collectively, they produced a faint but pervasive radio hum that should, in theory, still be traveling through the cosmos today. The incredible power of this 21-centimeter signal is that it acts as a universal clock and a cosmic thermometer. Because the universe is expanding, this signal from different eras gets stretched or redshifted by different amounts. The signal from hydrogen when the universe was 100 million years old arrives at Earth stretched to a much longer wavelength than the signal from when the universe was 500 million years old. By tuning our radio telescopes to different wavelengths, we can effectively slice the universe into thin chronological layers, creating a three-dimensional movie of the cosmos as it evolved from the Dark Ages through the era of the first stars and reionization. We could watch the story unfold frame by frame. This signal doesn't just tell us where the hydrogen was, it tells us what was happening to it. If the hydrogen gas is colder than the cosmic microwave background radiation, it will appear in absorption against that background glow. If it's hotter, it will appear in emission. The light from the first stars and galaxies would have heated the surrounding gas, first through their ultraviolet radiation, and then more dramatically through X-rays from early black holes. By mapping the changing temperature of the hydrogen gas, we could pinpoint exactly when and where the first sources of light switched on and how their influence spread through the cosmos. It would be the most direct possible window into the timeline of cosmic dawn. However, detecting this signal is arguably one of the most difficult challenges in all of modern astronomy. The primary obstacle is that the cosmological 21-centimeter signal is incredibly faint, about 10,000 times weaker than the foreground radio noise coming from our own galaxy and from human civilization. It's like trying to hear a pin drop in the middle of a roaring heavy metal concert. Our Milky Way galaxy blasts out radio waves across a wide range of frequencies, creating a bright, confusing foreground that must be meticulously subtracted. This requires not just sensitive telescopes, but an exquisite understanding of the galactic emission itself. Even the tiniest error in this foreground removal could completely swamp the subtle signal we're searching for. This immense challenge has spurred the development of some of the most ambitious astronomical projects ever conceived. Arrays of thousands of simple radio antennas are being deployed in remote, radio-quiet locations like the deserts of South Africa and the outback of Western Australia. Projects like the Hydrogen Epoch of Reionization Array and the Low-Frequency Array are already collecting vast amounts of data, pushing the limits of our data processing capabilities. But the ultimate instrument for this search is the Future Square Kilometer Array. When completed, the SKA will constitute the largest radio telescope on Earth, with a total collecting area of over 1 square kilometer spread across 2 continents. Its sheer sensitivity and resolution are designed to not only detect the 21-centimeter signal, but to map it in fine detail, transforming it from a simple detection into a rich source of cosmological information. The potential insights are revolutionary. A successful map of the 21-centimeter signal would allow us to see the bubbles of ionized gas created by the first stars and galaxies as they grew and overlapped, providing a direct test of whether stars or quasars were the primary drivers of reionization. It could reveal the very first stirrings of structure formation, showing how the dark matter distribution influenced the clumping of hydrogen even before the first stars ignited. It might even allow us to probe the properties of dark matter itself, as different dark matter models predict subtle differences in how the first structures formed. The 21-centimeter line is more than just a signal. It is a direct link to the neutral gas that witnessed the birth of the first light, offering us a chance to listen in on the universe's most formative era. To truly grasp the origins of the first stars, we must journey back even further beyond the Dark Ages, beyond the Big Bang's fiery afterglow, to an era so early it defies imagination. This brings us to our 19th mystery, a concept that is as profound as it is strange, the role of cosmic inflation. The universe we observe is vast, structured, and remarkably uniform on the largest scales. The cosmic microwave background radiation, a snapshot of the universe at 380,000 years old, shows a sky that is almost perfectly the same temperature in every direction. How did such smoothness and large-scale structure emerge? The leading theory is that the universe underwent a period of exponentially rapid expansion when it was only a tiny fraction of a second old, ballooning from a subatomic speck to something much larger in an inconceivably short burst. This was not an explosion into space, but a runaway expansion of space itself. The critical link to our story is that this inflationary period did more than just stretch the cosmos. It also planted the very seeds for all future structure. According to the theory, the vacuum of space during inflation was not perfectly calm. It was fizzing with quantum fluctuations, tiny, temporary changes in energy that are a fundamental property of reality at the smallest scales. As space inflated at a staggering rate, these microscopic quantum jitters were stretched to astronomical sizes, frozen into the fabric of the universe as minute differences in density. Imagine a perfectly smooth balloon. Now imagine blowing it up so rapidly that the tiniest microscopic imperfections on its surface are magnified into hills and valleys. Inflation did precisely this to the newborn cosmos. Those magnified quantum fluctuations became the slightly denser regions and slightly emptier voids that would, hundreds of millions of years later, serve as the gravitational anchors for the first dark matter halos and eventually the first stars. Without inflation's creative act of magnification, the universe might have remained forever smooth and featureless, a cosmic soup with no recipe for building stars or galaxies. The properties of the inflationary process itself, its duration, its energy determine the specific pattern of these initial wrinkles, a pattern we can still read today in the cosmic microwave background. This leads us directly to our 20th mystery, which asks a deeply technical but crucial question about the character of those initial cosmic seeds. The simplest models of inflation predict that these primordial density fluctuations should follow what mathematicians call a Gaussian or random distribution. In a Gaussian field, the fluctuations are completely random and symmetric. The likelihood of finding an extremely dense region is exactly the same as finding an extremely empty one, and there are no unexpected correlations or patterns between different fluctuations. It's a bit like the static on an old television screen, a purely random noise. This simple, elegant prediction has held up remarkably well when compared to the large-scale patterns seen in the cosmic microwave background by satellites like Planck. However, as our observations become more precise, astronomers are searching for tiny deviations from this perfect randomness, something known as non-Gaussianity. Finding even a hint of non-Gaussianity would be a monumental discovery because it would tell us that the physics of inflation was more complex than our simplest models suggest. Perhaps there were multiple fields of energy driving the expansion, interacting with each other in ways that left a distinctive fingerprint on the density fluctuations. Or maybe inflation did not proceed as a single, smooth event, but involved phases or transitions that created subtle correlations between different regions of space. A non-Gaussian signal would be like hearing a faint, repeating melody within the television static, a hint of order within the chaos, pointing to a richer and more complicated story for the universe's first moments. Where can we look for this signal? The answer lies in the pattern of the first galaxies. The initial distribution of density fluctuations dictated where the first structures would form. If the fluctuations were perfectly Gaussian, the clustering of the very earliest galaxies we observe with the James Webb Space Telescope should follow a specific, predictable statistical pattern. But if there is non-Gaussianity, we might see unexpected features, perhaps an overabundance of incredibly massive and bright galaxies at very early times, or peculiar arrangements of galaxies that seem to be correlated in ways that simple randomness cannot explain. These ancient galaxies are the direct descendants of those first inflationary seeds, and by mapping their distribution in the young universe with exquisite detail, we are effectively conducting a forensic analysis of the Big Bang's trigger. The hunt for non-Gaussianity is therefore a bridge connecting the grandest scales of cosmology, governed by the laws of inflation, to the detailed architecture of the first stellar systems, offering a chance to peer into the physics that operated at energies far beyond the reach of any particle accelerator on Earth. Now we arrive at a puzzle that is less about grand cosmic forces and more about a critical, practical bottleneck. We've talked about the immense power of the first stars and quasars and their role in burning off the hydrogen fog during reionization. But there's a fundamental obstacle we haven't yet considered. How did their powerful radiation actually break free to do its work on a cosmic scale? This is our 21st mystery, the great escape of ionizing radiation. Think of a massive newborn star blazing at the heart of its natal cocoon, an incredibly dense cloud of primordial hydrogen and helium gas. This gas is not a passive bystander, it's an effective prison for the very light the star is producing. Ultraviolet photons, the kind needed to rip electrons from hydrogen atoms, are easily absorbed by neutral hydrogen. In a dense environment, a photon might only travel a tiny distance before being swallowed by another atom, its energy converted into heat locally. For the star to influence the vast intergalactic medium, its ionizing radiation must first fight its way out of its own crowded neighborhood. If the gas is too thick, the star's light could be almost completely trapped, like a brilliant lighthouse whose beam is obscured by a dense, impenetrable fog. The star would be a spectacular but ultimately isolated phenomenon, its universe-changing power contained. The key factor here is what astronomers call the escape fraction, the percentage of ionizing photons that actually manages to leak out into intergalactic space. This is not a minor detail, it is a critical yet poorly understood variable that can make or break our models of how reionization proceeded. So, how did the first stars and galaxies solve this problem? The most likely answer involves a powerful combination of stellar feedback and cosmic construction. One of the primary mechanisms is the force of stellar winds. The most massive stars don't just shine, they blast the space around them with a torrent of charged particles flowing from their surfaces at tremendous speeds. These winds act like a cosmic sandblaster, relentlessly pushing against the surrounding gas, carving out vast cavities and low-density bubbles. Over thousands of years, these bubbles can expand, clearing a path through the dense gas. Once a channel is opened, ionizing photons can stream out along these cleared corridors, much like sunlight finally breaking through a hole in the clouds. The bigger and more powerful the star, the more effective its winds would be at this demolition work. But the most dramatic and effective escape mechanism was likely the star's own death. A supernova explosion is an event of almost unimaginable violence, unleashing more energy in a few seconds than the star may have emitted over its entire lifetime. The blast wave from a supernova travels outwards at a significant fraction of the speed of light, violently sweeping up the surrounding gas and ejecting it far into space. This doesn't just create a bubble, it can effectively blow the entire birth cloud to smithereens, completely dismantling the star's gaseous prison and unleashing a flood of previously trapped radiation. Furthermore, the explosion itself produces a tremendous burst of ionizing photons, which now have a much clearer path to travel. In a sense, the star's final sacrifice was the ultimate act of liberation for its light, ensuring that its energy could finally travel across the cosmos to ignite the process of reionization. The geometry of the early galaxies also played a crucial role. The first galaxies were likely not the neat, symmetrical spirals we see today. Instead, they were messy, turbulent, and porous structures, with clumps of stars and vast chimneys or tunnels carved by the combined effects of multiple stellar winds and supernova. This patchy, Swiss cheese-like structure is thought to be far more effective at allowing radiation to escape than a smooth, dense sphere of gas. Photons could find their way out through the holes and fractures in the galactic gas, a process that might have been far more efficient in these primordial, chaotic environments than in more settled modern galaxies. The escape fraction, therefore, wasn't a fixed number. It varied dramatically from object to object and evolved over time as galaxies grew and their structures changed. Pinpointing its average value is one of the biggest challenges in accurately simulating the epoch of reionization, as a small change in this parameter can completely alter the predicted timeline for how quickly the universe became transparent. The brilliant but brief reign of the population 3 stars could not last forever. Their very success contained the seeds of their own demise, leading us to the poignant mystery of their end. This wasn't a simple extinction event, it was a fundamental transformation of the cosmos, a changing of the guard dictated by the very elements these first stars created. As they lived their short, violent lives and died in spectacular supernova, they performed the universe's first act of large-scale recycling. They took the pristine hydrogen and helium from the Big Bang and forged it into something new, the first heavy elements, what astronomers call metals. With each explosion, these freshly minted atoms, carbon, oxygen, silicon, iron, were blasted out into the surrounding gas clouds, forever changing their chemical composition. This act of cosmic pollution marked the beginning of the end for the Population 3 era. The critical change was in how gas could behave. Remember, the reason Population 3 stars were so massive was that the pure hydrogen and helium gas had almost no way to cool down and fragment. Molecular hydrogen was a terribly inefficient coolant, but with the introduction of even a tiny amount of heavier elements, everything changed. Elements like carbon and oxygen can form dust grains, and these microscopic particles are incredibly effective at radiating away heat. More importantly, atoms of heavy elements themselves can cool the gas by emitting light at specific wavelengths when they are collisionally excited. This new, efficient cooling mechanism was a game changer. Suddenly, a collapsing cloud of gas could shed its gravitational energy much more effectively. It could become denser and, crucially, it could fragment into much smaller clumps. The era of the monolithic 100 solar mass Titan was over. The universe could now form stars that were smaller, more stable, and far more numerous, the Population 2 stars that we still see in our galaxy's halo today. This raises a central question about the nature of this cosmic transition. Was it a sharp, definitive cutoff or a long, drawn-out fade? Did the first generation of stars disappear everywhere at once, or did their reign persist in certain corners of the cosmos? One scenario suggests a relatively rapid and universal shift. In this view, the supernova ejecta from the very first stars mixed with the surrounding gas surprisingly quickly, perhaps driven by the immense energy of the explosions themselves and the large-scale flows of gas into the first dark matter halos. This could have created a fairly uniform and swift rise in metallicity across vast regions of the early universe. Once the metal content reached a critical threshold, a value astronomers refer to as a metallicity floor, the conditions necessary for forming a pure Population 3 star simply vanished. The universe would have switched almost entirely to producing Population 2 stars in a cosmologically short period. However, an alternative, more gradual picture is equally plausible. The early universe was not a perfectly mixed soup. It's easy to imagine vast, pristine reservoirs of gas that remained untouched by the pollution from the first supernova for a considerable time. While some regions were quickly enriched, others, perhaps in more isolated voids or on the far outskirts of the first protogalaxies, could have retained their primordial purity. In these cosmic backwaters, the old rules might have still applied. Population 3 stars could have continued to form, isolated behemoths igniting long after their siblings in more active regions had died out and given way to the new generation. This would mean that the Population 3 era did not have a single end date. Instead, it flickered out in different places at different times, a slow sunset rather than a sudden switch being thrown. This possibility makes the hunt for a surviving Population 3 star one of the most thrilling quests in modern astronomy. While it's incredibly unlikely that any of the original, monstrously massive stars survived, they burned out billions of years ago, there is a tantalizing chance that some lower mass Population 3 stars might still be shining. If the initial mass function of the first stars had any breadth at all, it's conceivable that a few stars with masses similar to our Sun could have formed. These stars, with their pure hydrogen and helium composition, would have incredibly long lifespans, potentially lasting for the entire age of the universe. Finding just one would be like discovering a living fossil from the cosmic dark ages, a pristine relic that could tell us everything about the conditions of the very first star formation. The search for these elusive objects is focused on our own galactic backyard. Astronomers scour the halo of the Milky Way, looking for the most extremely metal-poor stars known as ultra-metal-poor or even hyper-metal-poor stars. The current record holder is a star known as SMSSJ0313-6708, which has an iron content more than 10 million times lower than that of our Sun. Yet, crucially, it is not entirely metal-free. It possesses a tiny but detectable amount of heavier elements, indicating that it formed from gas that had been polluted by just a single previous supernova. This tells us it is a second-generation star, not a true first-generation pioneer. The Holy Grail would be to find a star with no detectable metals whatsoever. Such a discovery would confirm that low-mass population 3 stars did form, and that we have a direct window into the universe's first chapter. Every new, extremely metal-poor star discovered pushes the limits of our understanding and brings us closer to answering the profound question of when and how the universe's first light finally faded into history. Scattered throughout the halo of our Milky Way, and indeed around most large galaxies, are cosmic time capsules of astonishing density and age. These are the globular clusters, shimmering spheres, each containing hundreds of thousands, sometimes millions, of stars all bound together by gravity in a volume that is incredibly small by galactic standards. To put their density in perspective, if you were to live on a planet near the center of a globular cluster, your night sky would be ablaze with thousands of stars as bright as Venus is in our own sky, creating a perpetual starry twilight. The stars within these clusters are among the oldest objects we can study directly, with many dating back to within a billion years of the Big Bang. This makes them not just ancient, but living relics from the era of the first galaxies. The profound mystery is where and how these incredibly dense stellar cities themselves were born. Did they form as independent island universes, only later being gravitationally captured by the growing galaxies we see today? Or were they constructed from the inside out as the first building blocks within the protogalaxies themselves? The answer is more than a matter of historical curiosity. It holds the key to understanding the extreme environments where the earliest stars were made. One compelling line of thought suggests that globular clusters were actually the first true galaxies, or at least their dense cores. In this top-down scenario, the largest dark matter halos to collapse in the early universe didn't just form stars, they formed them in an incredibly concentrated burst. Imagine a vast cloud of primordial gas falling into one of the most massive gravitational wells available at the time. The conditions could have been perfect for a phenomenon known as a runaway starburst, where star formation occurs at an efficiency and pace that is simply unimaginable in the modern universe. In this frenzied environment, stars would have been born packed extraordinarily close together from the very beginning. This dense stellar swarm, still embedded in its dark matter halo, would have represented one of the first stable structures in the cosmos, a miniature galaxy in its own right. Over billions of years, as larger galaxies like our Milky Way assembled through mergers, these primordial globular clusters would have been swallowed whole, their dark matter halos stripped away by tidal forces, leaving behind the bright, dense ball of stars we observe today. This idea paints them as the surviving nuclei of the first generation of small galaxies that were mostly devoured, their outer stars torn away and assimilated into the larger galaxy's halo. However, a contrasting and perhaps more widely supported theory places their birth squarely within the tumultuous environment of the first protogalaxies. This bottom-up model proposes that globular clusters formed as singular, spectacular events inside the gaseous disks of the earliest galaxies. In this view, the key ingredient was not just gravity but turbulence. The first galaxies were chaotic places with massive inflows of gas, frequent mergers, and powerful shockwaves from the first supernova. Within this maelstrom, giant, dense clouds of gas could be compressed to unprecedented degrees. When such a cloud crosses a critical density threshold, it can collapse globally, igniting a firestorm of star formation in which a huge percentage of the gas is converted into stars in one go. The resulting cluster would be born dense, a sparkling jewel formed within the larger, more disorganized structure of the young galaxy. A crucial piece of evidence for this model is that we see globular clusters forming today in the aftermath of galaxy collisions, where similar conditions of extreme gas compression are replicated. This suggests the process is a fundamental mode of star formation under extreme pressure, a mode that was likely far more common in the violent early universe. The true value of these ancient clusters, however, goes far beyond their origin story. They act as fossilized records of star formation conditions in the primordial universe. Because all the stars in a given cluster formed from the same parent cloud at roughly the same time, they share a common age and chemical composition. By studying the distribution of stars within a cluster, how many high-mass stars versus low-mass stars it contains, astronomers can effectively determine its initial mass function, the blueprint for its birth. This is where the connection to the first stars becomes electrifying. Many globular clusters show chemical anomalies that are very difficult to explain. For instance, some contain multiple generations of stars, with later generations showing enriched levels of elements like helium, nitrogen, and sodium, but not in elements like iron that are typically produced in supernova. This bizarre fingerprint suggests that the gas for these second-generation stars was polluted by the winds from a very specific type of massive, first-generation star within the same cluster. It's as if the cluster preserved the chemical signature of its own first stellar population, a population that might have included stars unlike any we see forming today. By decoding these ancient chemical patterns, we might be able to infer the properties of the stars that built the clusters, potentially getting a glimpse of the initial mass function from a time when the universe was fundamentally different. These dense stellar systems, shining quietly in the halos of galaxies, may therefore hold the best preserved evidence we have for the characteristics of the universe's earliest stellar generations. When we picture the birth of the very first stars, it's natural to imagine them as solitary titans, each one a lone beacon reigning over its own dark matter halo. This vision of cosmic solitude is compelling, but it might be fundamentally incomplete. Our 24th mystery confronts this image head-on by asking a deeply consequential question. Just how social were these stellar pioneers? In the modern universe, the majority of massive stars are not alone. They are born in binary or even multiple star systems, gravitationally bound partners that orbit a common center of mass. Was this also the case at the dawn of time, or did the unique, pristine conditions of the early universe favor the creation of isolated giants? The answer isn't just a matter of celestial demographics. It has profound implications for the entire energetic and chemical evolution of the cosmos. To understand why this question is so pivotal, we need to consider the extraordinary power of a binary partnership. A single massive star has a dramatic but relatively predictable life. It burns its nuclear fuel quickly and explodes. But when you put two massive stars in a close gravitational dance, their story becomes far more complex and impactful. The more massive of the two will evolve faster, expanding into a giant and beginning to transfer its outer layers onto its companion. This stellar cannibalism can dramatically change the fate of both stars. The donor star can be stripped down to its core, altering the type of supernova explosion it will produce. Meanwhile, the recipient star is rejuvenated, gaining mass and potentially becoming a hypermassive object that would never have formed in isolation. This mass transfer is a cosmic game of consequences, setting the stage for outcomes that are impossible for a single star. The most dramatic transformations occur at the end of their lives. If the binary system survives the first supernova, the result can be a pair of stellar remnants, like two neutron stars or a neutron star and a black hole locked in a tightening orbit. Their inevitable spiral and collision would create a cataclysm known as a kilonova, an event now understood to be the primary cosmic forge for the heaviest elements in the universe, including gold and platinum. Furthermore, if one star becomes a compact remnant like a neutron star and its companion is still a normal star, the intense gravity of the remnant can pull material from the living star, forming an accretion disk that glows with tremendous X-ray radiation. These X-ray binaries would have been powerful new sources of high-energy photons in the infant universe, contributing significantly to the heating of the intergalactic gas during the epoch of reionization. The presence of even a modest population of binary systems among the first stars would have injected a level of energetic diversity and chemical complexity into the early cosmos that a population of solitary stars simply could not provide. So, what does the physics of primordial star formation tell us about the likelihood of such partnerships? The key, as always, lies in the cooling and fragmentation of the collapsing gas cloud. Early simulations, which were relatively simple, suggested that the first protostellar clouds were so massive and monolithic that they collapsed directly into a single, enormous star. The inefficient cooling from molecular hydrogen seemed to prevent the cloud from breaking apart. However, as computer models have grown more sophisticated, incorporating more detailed physics like turbulence and the effects of rotation, a different picture has emerged. These advanced simulations show that a collapsing primordial cloud can, in fact, develop a complex internal structure. As the cloud spins, it can flatten into a disk, and within this disk, gravitational instabilities can create spiral arms and distinct clumps. These clumps can then independently collapse to form multiple stars that are born relatively close together. This suggests that binary and multiple systems might not have been a rarity at all, but perhaps a common feature of the first stellar nurseries. The implications of this possibility are staggering. If binaries were prevalent, the early universe would have been a much more violent and productive place. The rate of pair instability supernova, for instance, could have been different, as mass transfer between binary partners might have altered the final masses of the stars. The number of stellar mass black holes created would have been higher, and many of them would have been in binary systems, potentially merging much earlier than previously thought and seeding the growth of the first supermassive black holes. The chemical enrichment from kilonovae would have scattered heavy elements like gold into the primordial gas much sooner, meaning the second generation of stars could have been born with a more diverse elemental palette. The simple, linear story of a first generation of solitary stars giving way to a second generation is replaced by a far richer narrative of interconnected lives and deaths, where stellar partnerships fundamentally shaped the conditions for everything that followed. Determining the true prevalence of these first cosmic couples is therefore essential to accurately reading the fossil record of the cosmos imprinted in the oldest stars we can observe today. But the story of the first stars does not end with their spectacular deaths. In many cases, it was only the beginning of a new and even more influential phase of their existence. When the most massive of these giants collapsed directly into black holes, they set the stage for a complex and powerful relationship, a cosmic dialogue between creation and destruction that would shape the future of the cosmos. This brings us to our 25th mystery, which examines the intricate and uncertain feedback loop between the first stars and the very first black holes. Imagine the scene shortly after a massive population 3 star has exhausted its nuclear fuel. Its core collapses, and instead of a star annihilating pair instability supernova, it forms a black hole of perhaps several dozen solar masses. This newborn black hole is not dormant, it is ravenous. It sits at the heart of what was once the star's gaseous envelope, and it begins to pull in the surrounding material. As gas spirals inward at near light speeds, it forms a superheated accretion disk, a maelstrom of plasma that glows with incredible intensity, emitting fierce X-rays and ultraviolet radiation. At the same time, the intense magnetic fields and rotation of the disk can funnel some of the infalling material into powerful, focused jets that blast outward from the poles at relativistic speeds. This entire system becomes a beacon of extreme energy, fundamentally altering its environment. The central question is, what was the net effect of this energetic output on the nascent galaxy taking shape around it? The answer is a paradox, as this feedback could be both creative and destructive, a true double-edged sword. On one hand, the radiation and outflows from the accreting black hole could have a profoundly suppressive effect. The intense X-rays can heat the surrounding hydrogen gas to temperatures of tens of thousands of degrees, making it too hot to collapse under its own gravity. Think of it as a cosmic blowtorch keeping a pot of water at a rolling boil, preventing it from cooling and condensing. Meanwhile, the relativistic jets can plow through the galactic gas, violently sweeping it up and ejecting it into the intergalactic medium. This process can effectively starve the entire region of the raw material needed to form new stars, quenching star formation and potentially stunting the growth of the young galaxy. This negative feedback is a crucial ingredient in modern simulations, as it prevents galaxies from turning all their gas into stars too quickly, helping to explain why galaxies today have not consumed all their fuel. Yet, in a fascinating twist, the very same forces can also have the opposite effect. While the broad swaths of radiation heat the gas, the shock waves generated by the black hole's jets and outflows can travel through the interstellar medium like colossal sonic booms. When these powerful shock fronts encounter cooler, denser pockets of gas, they can compress them past the critical point needed for gravitational collapse. It's akin to the way a shockwave from a supernova can trigger the birth of new stars in a molecular cloud. Furthermore, as the hot gas blasted away by the black hole eventually cools in the vast halos surrounding galaxies, it can rain back down in cooler, dense streams, potentially fueling a new burst of star formation at a later time. This positive feedback suggests that the first black holes were not just agents of destruction. They may have also acted as architects, orchestrating the pattern and pace of star birth across the first galaxies. The profound uncertainty lies in determining which of these effects dominated and under what conditions. Was the feedback primarily negative, shutting down star formation near the galactic center? Or was it positive, creating a starburst on the galactic outskirts? The outcome likely depended on a delicate balance of factors: the mass of the black hole, the rate at which it was accreting gas, the density and distribution of the surrounding gas, and even the angle of its jets relative to the galactic disk. A slow, steady accretion might produce a gentle heating that regulates star formation, while a sudden, violent influx of gas could trigger a quasar-like outburst that fundamentally reshapes the entire galaxy. Understanding this early feedback loop is not just an academic exercise. It is the key to explaining the observed scaling relations between the mass of a galaxy's central black hole and the properties of its stellar bulge, a correlation that suggests a deep, co-evolutionary history stretching all the way back to cosmic dawn. The first black holes, born from the first stars, may have therefore set the fundamental rules for how galaxies grow and evolve, their ghostly gravitational influence reaching across billions of years to shape the universe we see today. The quest to understand cosmic dawn is not limited to the faint glow of the first galaxies. Sometimes the most revealing clues come from the most brilliant beacons in the early universe. This brings us to our 26th mystery, which focuses on objects of almost impossible power, quasars at record-breaking distances. Quasars are the intensely luminous hearts of distant galaxies, powered by supermassive black holes in a state of extreme feasting. As vast amounts of gas spiral into the black hole, it forms a superheated accretion disk that can outshine the combined light of every star in its host galaxy. Finding these cosmic lighthouses at the very edge of observable time presents one of the most severe challenges to our understanding of the early cosmos because their existence defies the clock. The key measure of their distance and age is redshift, denoted by the letter Z. The higher the redshift, the further back in time we are looking. For decades, astronomers have been in a race to find quasars at redshifts beyond 7, meaning we see them as they were when the universe was less than 800 million years old. And they have succeeded, discovering objects like the quasar known as J031-0121, which holds the staggering redshift of 7.64. We see this quasar as it was just over 670 million years after the Big Bang. The sheer fact that it is visible at all is astonishing, but the real shock lies in the properties we can deduce from its light. By analyzing the width of specific emission lines in its spectrum, astronomers can estimate the mass of the central black hole. For this quasar and others like it, the answer is mind-bending: a black hole weighing well over 1 billion times the mass of our Sun. This is where the mystery deepens into a genuine cosmic conundrum. 1 billion solar mass black hole existing so early in cosmic history presents a monumental feeding problem. Let's assume the seed for this monster was a black hole left behind by the death of one of the first population 3 stars with a mass of, say, 100 solar masses. For it to grow to 1 billion solar masses in just a few 100 million years, it would have to consume matter at a ferocious, continuous rate, right at the theoretical limit of what is physically possible. This limit is called the Eddington limit. It's the point at which the intense radiation pressure from the infalling matter pushes back so strongly that it threatens to choke off the fuel supply. To reach such an immense size so quickly, this black hole would have needed to accrete matter at or above this Eddington limit for almost its entire existence, without any significant pauses. It's a feat of cosmic gluttony that is difficult to reconcile with our models, which suggest that accretion is often a messy stop-start process, interrupted by feedback and the limited availability of gas. The existence of these early giants forces astronomers to consider more exotic solutions. Perhaps the initial seeds were not stellar mass black holes at all, but were instead born much larger. This brings us back to the theory of direct collapse black holes. In this scenario, an immense cloud of pristine gas could collapse under its own gravity, bypassing the star formation stage entirely and condensing directly into a black hole with a starting mass of 10,000 or even 100,000 solar masses. A seed of this size would have a tremendous head start, requiring a much less frantic, and therefore more plausible, accretion rate to reach 1 billion solar masses by the time we observe it. Alternatively, perhaps early black holes found ways to accrete in super Eddington bursts, where radiation is trapped by the sheer density of the inflowing gas, allowing for short periods of hyper-efficient growth that bypass the usual limits. Each new record-breaking quasar discovered by powerful instruments like the James Webb Space Telescope and large ground-based sky surveys acts as a crucial stress test for our theories. These objects are not just curiosities, they are extreme laboratories that probe the fundamental physics of black hole growth and the conditions in the densest regions of the early universe. Finding a quasar at a redshift of 8 or even 9 would push the timeline back even further, intensifying the challenge and potentially ruling out some of the more conservative growth models. The search for these most distant quasars is therefore a race to understand the upper limits of possibility, forcing us to continually refine our ideas about how the most massive structures in the universe could have assembled themselves in what seems, from our cosmic perspective, like the blink of an eye. The story of cosmic reionization is often told as a simple, linear narrative. A dark universe slowly fills with light until the fog is gone. but the reality was almost certainly far more complex and uneven, a cosmic drama that unfolded differently from one region of space to the next. This brings us to our 27th mystery, which asks about the fundamental texture of this great transition. Was reionization a smooth, uniform process like a gentle global tide rising to cover the land? Or was it a patchy, clumpy affair, more akin to watching individual campfires ignite across a dark landscape, each one slowly burning back the surrounding undergrowth until the separate fires finally merged into a single conflagration? The answer to this question, the topology of reionization, holds crucial clues about the very sources that powered this cosmic revolution. To visualize the patchy scenario, think of the early universe not as a uniform sea, but as a block of Swiss cheese. Each piece of cheese represents the vast, cold, neutral hydrogen gas that still filled most of space. The holes in the cheese are the ionized bubbles. The first stars and galaxies acted like cosmic heating elements, each one creating a small, hot bubble of ionized plasma around itself. Inside this bubble, the hydrogen fog has been cleared and light can travel freely. Outside, the darkness and neutrality persist. In this model, reionization is not a synchronized global event. It starts at different times in different places, depending on where the first luminous objects happen to form. Over millions of years, these individual bubbles expand as new stars ignite within them, and as their radiation pushes the boundaries outward. Eventually, the bubbles touch, their edges merging to form larger, irregularly shaped ionized regions. The final stages of reionization would have involved these large regions connecting, with the last vestiges of neutral hydrogen persisting in the cosmic equivalent of deep valleys and remote islands before being finally evaporated away. The alternative, a smooth and uniform reionization, would require a very different kind of trigger. For the process to be globally simultaneous, the ionizing radiation would need to be extremely evenly distributed across the cosmos. This is difficult to achieve if the primary sources were individual galaxies and quasars, which are by nature clustered and unevenly distributed. A smooth process might point toward a dominant role for a truly pervasive and uniform source of ionizing photons, something that remains highly speculative, like the collective light from a vast population of decaying or annihilating exotic particles. For this reason, most astronomers strongly favor the patchy model, as it aligns perfectly with our understanding of how structure formed in the universe through the gravitational clustering of matter into galaxies that were themselves clustered into filaments and nodes. This is precisely why mapping the topology of reionization is so important. The size, shape, and distribution of those ionized bubbles are a direct reflection of the sources that created them. Imagine trying to deduce the nature of a light source by looking only at the shadow it casts. A few large, brilliant quasars would create a small number of very large bubbles relatively quickly. Their intense radiation could punch through the neutral hydrogen, creating vast ionized regions that might dominate the landscape. The topology in this case would be characterized by large, isolated clearings separated by wide swaths of neutral territory. On the other hand, if reionization was driven primarily by a countless population of smaller, fainter galaxies, the picture would be entirely different. The process would begin with a fine-grained froth of countless tiny bubbles, each one surrounding a small protogalaxy. These bubbles would be slow to grow and would only gradually begin to overlap, creating a much more intricate and finely textured pattern. The difference is like comparing the large, distinct clearings made by a few powerful spotlights to the delicate, interconnected foam created by millions of tiny sparks. This is where the promise of 21-centimeter astronomy becomes truly transformative. While telescopes like James Webb look for the individual galaxies, the 21-centimeter observations aim to map the gas itself. By tuning to different frequencies corresponding to different redshifts, a powerful radio telescope like the Future Square Kilometer Array could create a three-dimensional map of the hydrogen gas's state throughout the entire epoch of reionization. We wouldn't just see a list of galaxies, we would see the ionized bubbles they created as expanding voids in the neutral hydrogen. The statistical properties of these voids, their typical size, how they cluster together, and how their size distribution changes over time, would be the definitive signature of the topology. If the bubbles remain small for a long time before rapidly merging, it points to small galaxies. If a few very large bubbles appear early on, it strongly implicates quasars as the primary drivers. Unlocking this topological map would do more than just solve the mystery of the ionizing sources. It would provide a direct, dynamic view of one of the most important phase transitions in cosmic history. We could watch the universe flip from opaque to transparent, not as a theoretical concept, but as an observable, evolving structure. It would reveal the demographics of the first luminous objects in a way that counting individual galaxies cannot, telling us about the countless faint sources that are too dim for even our most powerful telescopes to see directly. The topology of reionization is the missing link between the catalogue of early galaxies and the large-scale transformation of the intergalactic medium, a ghostly imprint of the first great battle between light and darkness that shaped the transparent universe we inhabit today. The death of a population 3 star was not a quiet fade into darkness. It was a universe-altering detonation that fundamentally reshaped the cosmic landscape. When these titanic furnaces exhausted their nuclear fuel, their final moments unleashed energies that dwarf anything in our modern cosmos. A typical supernova today is a spectacular event, but the first supernova were in a class of their own. For the very largest of these stars, their death throes likely resulted in a pair instability supernova, an explosion so profoundly violent that it completely obliterated the star, leaving behind no black hole or neutron star. The sheer force of these blasts is almost beyond comprehension, releasing as much energy in a few seconds as our Sun will over its entire 10 billion-year lifespan. This wasn't just a star dying, it was a cosmic bomb going off in the pristine silence of the early universe, and its shock waves are still echoing through time. The most famous legacy of these explosions is their role as the universe's first alchemists. Inside the searing cores of these massive stars, nuclear fusion had been busily fusing hydrogen into helium, and then helium into heavier elements like carbon and oxygen. For the first time in history, the universe was creating something more complex than the basic ingredients of the Big Bang. But these newly forged elements were trapped deep within the star's interior. The supernova explosion was the great liberator, blasting this enriched material out into the void at incredible speeds. This act of cosmic recycling scattered the first seeds of complexity, the carbon for future life, the oxygen for future water, the silicon for future planets across vast regions of space. The gas clouds that would eventually form the next generation of stars were no longer pristine. They were now lightly salted with these heavy elements, a contamination that would forever change the rules of star formation. Yet the dispersal of these first metals was only part of the story. The supernova injected an even more transformative ingredient into the cosmos: raw energy. Imagine a shockwave of unimaginable power rippling outwards from the explosion, slamming into the surrounding clouds of cool, neutral hydrogen gas. This energy did not just gently push the gas, it heated it to temperatures of millions of degrees, transforming it into a hot, ionized plasma. This heating had a dramatic effect on the ability of small dark matter halos to form stars. In the earliest days, even a relatively small clump of dark matter could gather enough gas to potentially ignite a star. But after the first wave of supernova, the game changed. The intense heat from these blasts increased the pressure of the gas dramatically. For a small dark matter halo with a weak gravitational pull, this increased pressure was a death sentence. It could no longer hold onto its gas. The heated material would simply evaporate away, or be violently pushed out in a process known as supernova feedback. This feedback mechanism acted as a form of cosmic regulation. It effectively set a new, higher mass threshold for star formation. Only the largest, most massive dark matter halos with gravitational wells deep enough to withstand the supernova-driven winds could continue to collect gas and form new stars. The smaller halos were sterilized, their star-forming potential quashed. This had a profound impact on the pace and distribution of cosmic structure growth. It meant that star formation began to shift from being a widespread, fine-grained process to one that was more concentrated in the larger, more resilient potential wells. In essence, the first supernova helped to orchestrate the transition from a universe filled with tiny, isolated stellar beacons to one dominated by larger, more organized galactic structures. They weeded out the weak and fortified the strong, shaping the hierarchy of the cosmos we see today. The final, and perhaps most subtle, consequence lies in the specific elemental yield of these explosions. The pattern of elements produced by a pair instability supernova is theorized to be unique. Because the entire star is vaporized, the entire contents of its interior are scattered, resulting in a very distinct chemical signature compared to a core collapse supernova that leaves a remnant behind. This signature is like a fingerprint. Astronomers search for this fingerprint today in the atmospheres of the most ancient, metal-poor stars in our galaxy's halo. Stars that formed from gas polluted by only one or two of these first supernovae. Finding a star with this peculiar chemical pattern would be the ultimate confirmation of the existence and nature of these first stellar giants. It would tell us not just that they existed, but exactly how they lived and died, allowing us to measure their immense mass and energy directly from the fossil record they left behind. The impact of the first supernova was therefore both instantaneous and eternal. A blast wave that physically shaped their surroundings while simultaneously leaving a coded message about their own nature for us to decipher billions of years later. Now, as we chart the grand cosmic story from the first starlight to the galaxies we see today, we encounter a glaring discrepancy between what our most powerful computer models predict and what we actually observe in the night sky. This is our 29th mystery, a puzzle known as the missing satellites problem. Cosmological simulations, which meticulously follow the growth of structure from the tiny fluctuations in the Big Bang, paint a very specific picture of a galaxy like our Milky Way. They suggest that our galaxy should be surrounded by a vast swarm of tiny satellite galaxies, perhaps hundreds or even thousands of them, each one a small dwarf galaxy orbiting within the immense gravitational field of its larger host. These satellites are the surviving remnants of the first building blocks that merged to form the Milky Way, the cosmic equivalent of the stones left over after constructing a cathedral. But when astronomers conduct a census of the actual satellites around our galaxy, the numbers don't add up. We find only a few dozen of these dwarf galaxies, a fraction of what the simulations so confidently predict. It's as if we've calculated the precise amount of lumber needed to build a house, only to arrive at the construction site and find that most of the wood has simply vanished. This isn't just a problem for our local neighborhood. Observations of other large galaxies reveal a similar shortage of small companions. The universe seems to be missing a significant portion of its smallest galactic structures, and the question of where they went strikes at the heart of our understanding of how dark matter behaves and how the first stars influenced their surroundings. So, where did all these dwarf galaxies go? One of the most compelling solutions points an accusing finger back at the very topic of our exploration, the intense radiation from the first stars and galaxies. This idea centers on a process known as photoevaporation. In the earliest epochs, countless small dark matter halos did indeed form, just as the simulations predict. These halos, with their relatively shallow gravitational wells, began to pull in the surrounding hydrogen gas, setting the stage for the birth of their first stars. But before this process could get very far, the cosmic environment changed dramatically. As the first massive stars and quasars switched on, they flooded the universe with a background of energetic ultraviolet radiation. For the gas trapped in those small halos, this radiation was a catastrophe. The ultraviolet photons carried enough energy to violently heat the hydrogen gas. Imagine a small, shallow pond on a hot, sunny day. The sun's energy quickly heats the water, and some of it evaporates into the air. Now scale that up to a cosmic level. The ultraviolet radiation heated the gas within these vulnerable small halos, giving its atoms so much thermal energy that they could overcome the weak gravitational pull holding them there. The gas simply evaporated away, boiling off into the vast intergalactic medium. Without gas, there could be no star formation. These small dark matter halos were left as barren, invisible shadows still present, still orbiting their host galaxies, but completely dark and undetectable by our telescopes, which rely on starlight. In this scenario, the satellites aren't technically missing. They're just invisible, their potential for light extinguished before it could even begin. This explanation elegantly links the era of the first light directly to the present-day structure of galaxies. The radiation from cosmic dawn acted as a form of cosmic regulation, imposing a minimum size for a galaxy to form. Only halos massive enough to have a deep gravitational well, one strong enough to hold onto its gas against the onslaught of ultraviolet radiation, could successfully become the dwarf galaxies we see today. This process, often called suppression, effectively set a brightness floor for galaxies. It explains why we don't see a countless number of extremely faint, tiny galaxies swarming around the Milky Way. The smallest ones were sterilized by the ambient light of the first stellar generations. However, the story may be even more complex. An alternative, or perhaps complementary, explanation involves the very nature of dark matter. The standard cosmological model is built on cold dark matter, where particles move slowly, allowing them to clump efficiently on very small scales and produce a vast population of small halos. But if dark matter is slightly warm, meaning its particles have a bit more kinetic energy, the picture changes. Warm dark matter particles would be less likely to clump together on the smallest scales. This would mean that far fewer tiny dark matter halos would form in the first place, naturally leading to a lower number of satellite galaxies without needing as much radiative suppression. The missing satellites problem, therefore, isn't just about astrophysics. It's a potential window into the fundamental properties of the mysterious substance that makes up most of the matter in the universe. By precisely counting the dwarfs we can see and using new techniques to search for the invisible ones, we are conducting a crucial test that could reveal the true nature of dark matter itself. And so we arrive at the final, and in many ways most humbling, mystery in our journey. After exploring titanic stars, ghostly dark matter, and cosmic revolutions, we must now confront a barrier that is not just technological but fundamental. This is the ultimate limit of observation, the impenetrable veil that hangs over the universe's true infancy, the period known as the cosmic dark ages. For all our technological prowess, there is a chapter of cosmic history that traditional astronomy may never be able to read directly. To understand this barrier, we need to revisit the cosmic timeline. Our deepest, most reliable snapshot of the young universe comes from the Planck satellite and its observations of the cosmic microwave background. This fossilized light shows us the cosmos as it was at 380,000 years old, a time when the universe had cooled enough for atoms to form and light to travel freely for the first time. It is an invaluable picture, but it is just that a single, frozen moment. After that moment, the universe entered a long era of darkness. For the next 100 million years or more, there were no stars, no galaxies, no quasars. The cosmos was a silent, expanding sea of neutral hydrogen and helium gas, slowly cooling and gently being tugged by the invisible hand of dark matter. This is the cosmic dark age, and it is completely invisible to telescopes that rely on light. there was simply nothing there to see. No light was being emitted. This creates a profound gap in our knowledge, a chasm between our first baby picture of the universe and the moment the first starlight switched on. It's like having a photograph of a newborn child, and then the next picture we have is of them as a young adult. We have missed the entire childhood, the formative years where the personality and fundamental structures developed. During the Dark Ages, the tiny density fluctuations imprinted in the cosmic microwave background were slowly, silently being amplified by gravity. The dark matter scaffolding for the first galaxies was being assembled. The very first protostellar clouds were beginning to condense, but because this all happened in the dark, we have no direct window into these critical processes. We can only simulate them on computers and then check the results against the universe we see much later, after the lights have come on. The Dark Ages represent the ultimate cold case, a period without any eyewitnesses. A pressing question is, will we ever find a way to lift this veil? Is this a permanent boundary for scientific inquiry, or is there a faint signal we might one day detect? Our greatest and perhaps only hope lies not with light, but with the most common atom in the universe. As we discussed with the 21-centimeter line, the neutral hydrogen gas that filled the Dark Ages was emitting a faint radio hum. The expansion of the universe has stretched this signal so profoundly that what started as a 21-centimeter wavelength is now likely many meters long, placing it in the extremely low-frequency radio band. Detecting this specific signal from the heart of the Dark Ages before the first stars is the holy grail of modern cosmology. It would allow us to create a timeline, a movie of the universe's evolution during its silent phase. We could watch the gravitational growth of dark matter halos by mapping the subtle clumping of the hydrogen gas they were pulling in. We could potentially even see the ripples from sound waves that traveled through the early universe, frozen in the gas distribution. However, the technical challenges are beyond staggering. They are arguably the most difficult ever faced in science. The signal is unimaginably faint, buried under foreground radio noise that is thousands of times stronger. This noise comes from our own galaxy, from Earth's atmosphere, and even from human civilization. Furthermore, the Earth's ionosphere acts as a shield, blocking these extremely long wavelengths from reaching the ground. To have any chance of success, we would need to build radio telescopes of unprecedented scale in a location free of all interference, most likely on the far side of the Moon. The lunar far side is permanently shielded from the radio chatter of Earth, and its vacuum environment is ideal for observing these ultra-long wavelengths. Concepts for building a vast array of simple radio antennas in a lunar crater are already being studied by space agencies, a project that would represent a monumental leap in our quest to explore the cosmos. But even this might not be enough. The signal from the very earliest Dark Ages might be so weak and so redshifted that it blends into the fundamental noise floor of the universe itself. There may be a point, a redshift so high that the information is truly lost forever to the phenomenon of cosmic expansion. This possibility forces us to contemplate the limits of human knowledge. Some eras of the universe's history may be fundamentally unrecoverable, not due to a lack of ingenuity, but due to the basic laws of physics. The cosmic Dark Ages, therefore, stand as a permanent reminder of our place in the cosmos. We are creatures of a luminous era, born from stars that ignited long after the true beginning. Our view of the dawn of time will always be partially obscured, a testament to the fact that the universe holds secrets that may remain forever beyond our grasp, inviting us to forever wonder about the profound silence that preceded the first light. This grand journey through 30 cosmic mysteries ultimately brings us to a profound and deeply personal realization. We have chased the physics of collapsing gas clouds, the violent deaths of massive stars, and the intricate feedback loops of the early cosmos, but these are not merely abstract scientific puzzles. The quest to understand the first stars is, in its most essential form, the quest to understand our own origin story. every heavy element essential for life, the oxygen we breathe, the carbon that forms the backbone of our DNA, the iron that carries oxygen in our blood, was forged in the heart of a star that lived and died long before our sun was born. The calcium in our bones, the phosphorus in our cells, even the iodine necessary for our thyroid function, all were created in stellar furnaces and scattered across the galaxy by supernova explosions. The famous phrase, "we are stardust," is not just a poetic metaphor, it is a literal scientific truth. We are the universe become conscious, looking back on itself and trying to trace the steps of its own creation. This connection transforms astronomy from a distant science into a form of cosmic archaeology. When an astronomer points a telescope like James Webb at the most distant galaxy, they are not just collecting data on an alien object, they are reading a chapter from our own family history. They are searching for the ancestral home where the elements that built our world were first minted. Each new discovery about population 3 stars, about reionization, or about the assembly of the first galaxies adds another piece to the puzzle of how a universe of simple hydrogen and helium could eventually produce a planet teeming with life and creatures capable of wondering how it all happened. The sheer unlikeliness of this chain of events is staggering. It required the deaths of countless stars, the precise tuning of physical constants, and billions of years of cosmic evolution to create the conditions necessary for us to exist. Understanding this journey fosters a profound sense of connection to the cosmos, a feeling that we are not isolated observers but an integral part of a vast, evolving system. Yet, with every answer we uncover, the universe seems to unveil new, even deeper questions, pushing the boundaries of our understanding toward the truly fundamental. Confirming the existence of population 3 stars would be a monumental achievement, but it would immediately lead us to ask what came before them. What were the precise properties of the quantum fluctuations from inflation that seeded their formation, and what in turn caused inflation to begin? We can trace the chain of causality back to a fraction of a second after the Big Bang, but the ultimate question of why there is a universe at all, why there is something rather than nothing, remains firmly in the realm of philosophy. The nature of dark matter and dark energy, which together govern the expansion and structure of the cosmos, are complete mysteries. We do not know what they are, only that without them, the universe as we know it would not exist. Our story is still missing its most critical characters. This endless cycle of inquiry highlights a beautiful and humbling aspect of science. It is a perpetual journey, not a destination. The goal is not to arrive at a final, complete answer, but to continually refine our questions, to push the horizon of ignorance ever further back. The mysteries of the first stars and galaxies represent a frontier of knowledge that is uniquely powerful because it sits at the intersection of the empirically knowable and the profoundly existential. It challenges our tools, our intellect, and our imagination. As we continue to build ever more powerful telescopes and develop ever more sophisticated simulations, we are not just collecting facts. We are participating in an ancient human tradition of seeking our place in the grand scheme of things. The light from the first dawn is still traveling toward us, carrying with it the secrets of our beginning, and our relentless pursuit of that light is one of the most meaningful stories we can tell. And so this incredible journey through 30 cosmic enigmas brings us full circle, from the profound silence of the dark ages to the brilliant, chaotic dawn of the first light. We have seen how these mysteries are not isolated puzzles but interconnected threads in a single, grand tapestry. The immense mass of a population 3-star dictated its violent death, which in turn seeded the cosmos with the first heavy elements, polluting the primordial gas and forever changing the rules of star formation. That pollution influenced the very efficiency with which galaxies could form, while the radiation from those first stars and black holes began the epic battle of reionization, a process whose patchy topology reveals the nature of the sources that drove it. Every answer we uncover reveals a deeper layer of connection, painting a picture of a young universe that was dynamic, violent, and fiercely creative, governed by a beautiful and complex chain of cause and effect that set the stage for everything that followed. The launch of the James Webb Space Telescope marked a quantum leap in this quest, providing us with a window into epochs previously beyond our reach. Its deep-field images are not just pictures, they are portals to the universe's infancy, showing us galaxies that existed when the cosmos was a mere fraction of its current age. The data it provides on the chemical composition of these early objects, their masses, and their rates of star formation are like finding pages of a lost historical manuscript. Yet, for all its power, the first stars and galaxies remain profoundly elusive. We see their collective glow, we infer their presence from their chemical legacy in ancient stars, and we model their formation in vast supercomputer simulations. But a direct, unambiguous observation of a true first-generation star continues to dance just beyond the edge of detection. These celestial pioneers guard their secrets closely, their light stretched and faded over an unimaginable gulf of space and time. This is not the end of the story, but a thrilling new beginning. The mysteries that remain are beacons guiding the next generation of exploration. Engineers and scientists are already designing the telescopes that will follow Webb behemoths like the Habitable Worlds Observatory and ground-based giants like the Extremely Large Telescope, with mirrors so vast they will collect light with unprecedented sensitivity. In the radio spectrum, the square-kilometer array will soon listen for the 21-centimeter whisper from the Dark Ages, aiming to create a three-dimensional movie of the universe's transformation. At the same time, theorists are developing ever more sophisticated models, incorporating new physics and feedback mechanisms to better simulate the chaotic birth of the first structures. The path forward is a combination of technological marvels and intellectual bravery, each new tool and theory giving us a fresh chance to peel back another layer of cosmic history. Our exploration of the cosmic dawn is ultimately a celebration of human curiosity. It is a testament to our innate desire to look up at the night sky and ask, where did it all begin? The fact that we can use the laws of physics observed here on a tiny planet to understand events that occurred over 13 billion years ago is nothing short of miraculous. The journey to find the first light is one of the greatest adventures in science, a story that is still being written. We want to hear which of these 30 mysteries captured your imagination the most. Was it the potential existence of dark stars powered by the annihilation of unseen matter, or the cosmic chicken and egg problem of whether stars or galaxies came first? Let us know in the comments below. If you enjoyed this deep dive into the wonders of the cosmos, be sure to subscribe for more journeys to the edge of our understanding. The universe is full of secrets, and together we can continue to uncover them.